Semiconductor doping. Intrinsic semiconductors, often called pure semiconductors, have very few free electrons under normal conditions and so behave like insulators. At absolute zero, their valence band is full and there are no electrons within conduction band. As we increase the temperature up to ambient temperature, there are some electrons within the conduction band, so some conduction does take place. Most commonly, these are made of silicon and germanium, as we talked about in the semiconductor theory PowerPoint. Now, both of these materials, the germanium and the silicon, have a valency of 4. That is, they have 4 outer electrons available for bonding. So if we consider the electron diagram, here's our nucleus and we have 4 outer electrons. And normally these are in a crystalline structure and bonded together. All 4 of its outer electrons are bonded, and therefore there are very few free electrons available to conduct, making the resistance very large. So we can see here in the diagram, we have our silicon nucleus and we have our bonded electrons in a very regular crystalline structure. Although all the outer electrons are bonded and unable to move, if the crystal is heated or given other forms of energy, for example, illuminated with light, or we connect it to a potential and some of the electrons acquire some more energy, if they have sufficient energy, they can break their bonds and become available for conduction. When the electron escapes from the atom, it leaves behind a hole. That hole is positively charged because it's the absence of an electron. -1 is +1. This hole then can be filled by another electron from a neighboring atom, which will in turn leave a hole there. So the electrons skip from hole to hole to hole, and that allows for conduction. Because although it's technically the electron that moves, the effect is the same as if the hole that moves through the crystal lattice. So we see our electrons and we see the hole. The electron moves to fill the hole, leaving a hole behind. The hole appears to have moved right, however, it's actually the electron that has moved left. In an undoped semiconductor, the number of holes is equal to the number of electrons. Therefore, we tend to have only a very, very small amount of movement. Current consists of drifting electrons in one direction and drifting holes in the other. In extrinsic semiconductors, they are formed by adding controlled amounts of an impurity to the pure semiconductor. This is called doping. You have 2 types. The first one is the N-type. If an impurity such as arsenic, which has 5 outer electrons, is added to the crystal lattice, then 4 of its electrons will be used for the bonding with the other silicon atoms, and the 5th is free to move about. Doping has increased the ability of the crystal to conduct and therefore decreases resistance. That free electron allows for more electron hole movement to occur, and that's what causes a greater amount of conduction. So we see within the diagram, we have an arsenic nucleus with an additional electron around about the outside here, and that electron can move around, and the movement of that electron, the drifting of that electron, allows for conduction to take place. Since the electrons are negatively charged carriers, we call this an N-type semiconductor. The addition of the impurity atoms to the semiconductor, called doping, decreases the resistance. In an N-type semiconductor, we have majority negative charge carriers. Though it should be noted, the total number of protons and the total number of electrons in the material are the same. Therefore, even though we have an N-type material with majority N negative charge carriers, overall the material is electrically neutral. In the P-type semiconductor, we dope with an element, for example, indium, and that only has 3 outer electrons. This creates an additional hole. Now that additional hole means we can have more of a drift of electrons to fill that hole, therefore creating a hole behind it. An increased drift of electrons, or an increased drift of the holes, increases conductivity. An electron from the next atom can move into the hole, leaving behind another hole and a net positive charge on the atom. In effect, the positive hole appears to move through the semiconductor carrying a positive charge, when in actuality it's the negative electrons which are moving through. This is called the p-type semiconductor material, as most of the conduction takes place by the movement of positively charged holes. But again, overall the atom is electrically neutral because the number of protons and the number of electrons are the same. So, doping reduces the resistance of a semiconductor. The more doping that takes place, the more charge carriers are there. Each impurity atom gives one charge carrier. Although p-type and n-type semiconductors have different charge carriers, they are both neutral overall. That is, a metal can conduct but is normally neutral. Each type of semiconductor will have additional charge carriers which are free due to thermal ionization. So, in an intrinsic semiconductor, some conduction can take place with the addition of some thermal energy. That conduction will take place because electrons are given energy to break their bonds and leave a hole behind, and then another electron fills that hole and leaves a hole behind it, and so on and so forth. That always takes place. However, if we introduce an impurity, in the case of a p-type, an additional hole, then the majority of the charge carriers are holes and a minority of electrons. The additional holes allow for greater conductivity, greater movement of the electrons. In the n-type material, the majority charge carriers are electrons and a minority are holes. So there are more electrons free to move. The addition of impurity decreases resistance, irrespective of whether it's p-type or n-type, and some conduction will take place due to thermal energy in either an intrinsic or an extrinsic semiconductor material.